This is Lab 3, Magnetic Field of a Bar Magnet by Chandler Pittman. So, a little bit about our table of contents today. First, we'll kind of go through the introduction, which would be our equations and our experiment. Second would be our model. Third is going to be our calculations. And fourth is going to be that analysis and conclusion. So first, our introduction. So, what is the problem we are trying to solve? We are trying to solve for the directions and magnitude of the magnetic field at different points near and around a magnet. And why are we interested in it? It is helpful for explaining and understanding magnetic fields. So, a little about the equations we used today. We used the Biot-Savart law, the magnetic field of a dipole, and the distance dependence formula. And as can be seen below, these are all the different equations we used. So, a little bit about our experiment. First, using a phone app, we found out where basically the magnet chip was in our phone, and this was done by using this app, and we got our phone on the yardstick and found the absolute value of the x component when it was a maximum, and where the absolute value of the y component was a minimum, and then we did vice versa, so we could get a cross section to really find out where that chip was, so we could start the experiment. After doing that, we first measured the magnetic field from the magnet on axis, which would be parallel. And second, we found the magnetic field from the magnet off axis. So this would be at a 45-degree angle. And after completing our experiment, we got the following results. As you can see on the graph, we got a y equals negative 2.1818x minus 13.797. And we got a B net of 5.5219 e to the negative fifth. So after kind of calculating those values on our spreadsheet, we also decided to model it and write some code to see if it could match. So here's the model we created. So first you can see that function for that dipole B, as well as different arrows below it, which is just the observation of the axes and at the perpendicular. And after that was all coded out, we can see the results. So after we coded our model, we got the following results of this. We got a magnitude B at 45 degrees of 5.1339 e to the negative fifth. And if we can compare that to what we got on our spreadsheet, it's a little bit lower, as we got 5.5219 e to the negative fifth. So a little bit different, however very close. Next, we want to kind of do some calculations based off of our Excel document. So first, if you kind of, if you look at our document, we can see we had the line of y equals negative 2.1818x minus 13.797. And you're able to use that equation to get your n and your k. So now that we know our n and our k values from the Excel spreadsheet, we're able to calculate the magnetic dipole moment mu, which we got 5.1 amps per meter squared. Finally, we're kind of talking about some analysis and conclusion. So first, when answering the two what-if questions, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So first, our results would not be calibrated at all, messing up the final results. And secondly, Earth's magnetic field would be another variable needed to take into consideration, which would make it tough to calculate. And for our other what-if question, if you were to stick two identical magnets together end to end and run the experiment again, how would your measurements differ? What would you expect? And we would expect the magnitude of the field to be double. So some more observations that we made. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, which is true, as well as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And finally, when it kind of comes to some assumptions and errors that we could have made throughout this experiment, first it comes to making sure we had that correct magnetometer chip location. It could have been really faulty when we originally did it, which would have messed up the entire experiment. As well as faulty magnet. If it's not a very strong magnet, you're not going to get a very good value, and it won't be working as you would like to. It'll just be a lot smaller. And then we also assume that the magnetic field becomes less strong as distance increases, which isn't necessarily true. It could be in some cases, however, it isn't always true. And yeah, that's all for today.